Okay, welcome to screencast number 2 for chapter 19, and we're discussing fossil fuels and their impacts and energy conservation. So at the end of the last screencast, we were talking about EROIs, and this is energy returned on investment. And what we were talking about is the higher the EROI ratios means that we receive more energy from each unit of energy that we invest. So fossil fuels, which are widely used because of their EROI ratios, have historically been high, but as we've seen, these ratios can change over time. Ratios rise as the technology to extract the process of fossil fuels improves, and they fall as the resources are depleted and the remaining resources become harder to extract. So the EROI ratios for producing conventional oil and natural gas in the United States actually declined from roughly a 30-to-1 ratio in the 1950s to about a 20-to-1 ratio in the 1970s. Today we're looking at around 11.1, which means that we used to be able to gain 30 units of energy for every energy expended, but now we can only gain 11. The EROI ratios for oil and gas decline because we've extracted the easiest deposits first, and now we must work harder and harder to extract the remaining amounts. So if we go back to that Alberta oil sands, the EROI ratios are still lower because oil sands are a low quality fuel that requires a great deal of energy to extract and process. The EROI estimates for oil sands from studies so far range from a 1.5-to-1 ratio to a 9-to-1, and most of the estimates are around 3-to-1 to 5-to-1. So here are two graphs that reflect the EROI values for discovering oil and gas in the United States, and what they've shown is how it's declined over the past century. So we can see both show a decline, a little bit of an up and down, but still continuing to go down. Well, the next question is, where do we turn for our energy in the future? We began by extracting the fossil fuel deposits that were readily located and accessed, and we took advantage of the boundless energy at cheap prices. Fossil fuel deposits are finite and finite and non-renewable, and we have gradually began to deplete them. And because of that, our EROI ratios rose and the fuels became much more expensive. We have developed new technologies to reach deeper and farther. We are expending more money and energy in order to continue obtaining fossil fuel energy. We've returned to sites that have already been extracted, bringing our new powerful machinery and approaches to squeeze more fuel from the known locations. Now we are reaching into formerly inaccessible places, drilling deeper, moving further offshore, and exploring the seabed of the Arctic. We're using more potent extraction methods, something called hydraulic fracturing, which we're going to talk about in the future. And this is a way of freeing gas from rock layers. We are perusing new types of fossil fuels, and these are including the oil sands that you read about, and shale oil and methane hydrates. These fuels are more expensive and they are lower in quality. Another way that we can respond to the depletion of our conventional fuels is developing clean ways of providing energy, clean, sustainable ways, using renewable resources like the sun and the wind and hydroelectric. We can gain energy that is sustainable in the long term, and we can greatly reduce pollution and health impacts and the emission of greenhouse gases that drive climate change. Our ability to control pollution has really lagged behind our capacity to consume energy. And many scientists are now warning that if we do not immediately step up energy conservation and accelerate our shift to renewables, that we will drive our planet's climate into unprecedented territory, threatening impacts on our economy, on our quality of life, and our society's future. So a lot to think about where we're headed. So the next part of the chapter, we're going to talk about fossil fuels, how they're formed, and how we extract them. So let's take a look at this. So the fossil fuels that we use today, were actually formed from organisms that lived about 100 to 500 million years ago. So a long, long time ago. Our energy originally came from the sun, and that was converted into chemical bond energy by the process of photosynthesis, and we've learned about that process. And chemical energy in these organisms' tissues then became concentrated as these tissues decomposed and their hydrocarbon compounds were altered and compressed. But most organisms after death do not end up as part of coal, gas, or oil deposit. For example, a tree that falls and decays as a rotting log on the forest floor undergoes mostly aerobic decomposition. There's the presence of air. Bacteria and other organisms use that oxygen to break down the plant and the animal remains into simpler carbon molecules that are then recycled through the ecosystem, those biogeochemical cycles that we talked about. Where fossil fuels, on the other hand, are done by anaerobic decomposition. And this involves little or no oxygen and dead organic matter that is already in the environment at the bottoms of lakes and swamps and shallow seas will undergo this anaerobic process. The organic matter that accumulates at the bottoms of these water bodies may be converted into crude oil, natural gas, or coal. And there's 4 things that will determine or depend on what they turn into. So 1, the chemical composition of the material. 2, the temperatures and the pressure to which it is subjected. 3, the presence or the absence of anaerobic decomposers. And 4, the passage of time. And it takes a long time to produce these fossil fuels. Taking a look at this graphic, fossil fuels begin to form when organisms die and end up in oxygen-poor conditions. So if this vegetation dies and gets into the water and sits at the bottom of the pond or the lake, then and other marine life can also sink and die and get to the bottom as well, then this is going to build up layers and layers of sediment. And the deeper it gets, the better the anaerobic conditions can be for decomposition. That pressure then, as everything builds up, and the biochemical changes that take place, the changing of these bonds, is how coal is going to form. So this can occur, as we talked about, when trees fall into lakes. Organic matter undergoes slow anaerobic decomposition, which you see in the middle of the diagram. Coal results when the plant matter is compacted so tightly that there's little decomposition, as we see in the bottom part of this picture. And the action of geothermal heating, which we see on the other side, can create crude oil and natural gas, which come to reside in porous rock layers beneath the dense, impervious layers of the earth. All right, so let's take a look at coal, which is the world's most abundant fossil fuel. It's a hard blackish substance that's formed from organic matter. Generally that matter comes from woody plant material. It has been compressed under very high pressure, creating this dense, solid carbon structure. Little decomposition takes place because the material cannot be digested or appropriate decomposers are not present. Proliferation of about 300 to 400 million years ago of swampy environments where organic material was buried has created coal deposits throughout the world. Coal varies from deposit to deposit in the amount of water, carbon, and potential energy that it contains. The organic material that is broken down anaerobically but remains wet near the surface and not well compressed is what we call peat. And peat decomposes further as it's buried under sediments, as heat and pressure increase and as time passes. This causes the water to be squeezed out and the carbon compounds are packed more tightly together, and this forms coal. Scientists classify coal into 4 types, as seen here in this picture. Lignite, which is the first type. Subbituminous, which is the second. Bituminous, and then anthracite, which is the really tightly compact. You can see that it's more porous as lignite, and then it gets more compact as it goes through and becomes anthracite. The more coal is compressed, the greater it is in carbon content and the greater energy content per unit volume that you're going to have. Okay, so here, this is just a review of what peat is. Talks about the additional pressure and the 4 types that it's classified in. All right, so our next, whoops, went one too far. Our next thing that we're going to talk about, and we only have about 2 minutes left in this screencast, are oil and natural gas. The sludge-like liquid that we know as oil or crude oil contains a mixture of hundreds of different types of hydrocarbon molecules. Natural gas is consisting primarily of methane and includes varying amounts of other volatile hydrocarbons. Oil we refer to as petroleum, but that term can also apply to oil and natural gas collectively. Both of these are formed from organic material, especially dead plankton that has drifted down through the coastal marine waters from millions of years ago and settled on the ocean floor. The organic matter is buried deeply, and there's pressure that's exerted by the overlaying sediments that are present. Carbon bonds in the organic material begin to break, and the organic matter forms a substance called kerogen. This acts as a source of material for both natural gas and crude oil. As more heat and pressure act on the kerogen to degrade the complex organic molecules into simpler hydrocarbon molecules, oil tends to form under temperature and pressure conditions. And these pressure conditions are about 1 to 2 miles below the surface, and at depths of 1.9 miles, and the high temperatures and pressures tend to form this natural gas. Natural gas that forms in this way from compression is referred to as thermogenic gas, and thermogenic gas may be formed directly, or it may also form coal. You've probably walked by a swamp and smelled swamp gas. This comes from anaerobic decomposition of organic matter, and this is another process that natural gas can be made by, known as biogenic gas. One source of biogenic natural gas is the decay process in landfills, and many landfill operators are now trying to sell this as fuel. So biogenic gas is nearly pure methane, whereas thermogenetic gas contains small amounts of other gases and methane. Okay, we're running out of time for this. We'll see you in the next screencast.